All right, in this video, we're going to talk about section 5.1 dealing with systems of linear equations in two variables. And in this section, we're going to decide whether an ordered pair is a solution to the linear system. We're going to be solving linear systems by substitution. Also, we'll solve linear systems by addition. And we're going to identify systems that do not have exactly one ordered pair solution. It could be a system where there is no solution that exists, or there could be infinitely many solutions that exist. Okay, so we'll start with systems of linear equations and their solutions. All equations in the form of ax plus by equal to c are going to be straight lines when you graph them on the coordinate plane. Two such equations are called a system of linear equations, or in short, a linear system. A solution to a system of linear equations in two variables is an ordered pair that satisfies both equations in the system. So like for this example, the ordered pair 3, 4 does satisfy this system here, which is x plus y equals 7 and x minus y equal -1. And we can verify that by letting x equal 3 and y equal 4. As in each equation, we just substitute the x and the y with those values here. So like in x plus y equals 7, we substitute the x with 3 and the y with 4. And if we add 3 plus 4, we should get 7, and we do. So that's true for the first equation. Now for the second equation, which is x minus y equal -1, again, we substitute the x with 3 and the y with 4. So here 3 minus 4 would give you -1, and it does equal to -1. So we can say that the ordered pair 3, 4 is a solution, or is the solution to that linear system. X plus y equals 7 and x minus y equal -1. All right, a system of linear equations can have exactly one solution or no solution, or it can have infinitely many solutions. So throughout this video, we're going to be dealing with systems of equations that can have one of these three possibilities. Okay, so now let's look at example 1. Let's say I want to consider the system 2x minus 3y equal -4, and 2x plus y is equal to 4. And we want to determine if each ordered pair is a solution to the system. So in part A, I got the ordered pair 1, 2. And I want to determine if that ordered pair is a is a solution to that system that we have here. So the ordered pair 1, 1, 2 is this. The first term is the x coordinate, so x will be equal to 1. The second is the y coordinate, that will be 2. And for each equation in that system, we're going to substitute the x with 1 and the y with 2. So the left side has to be equal to the right side on both equations. Not just one, it has to be both. So I'm going to start with 2x minus 3y equal -4. So again, I substitute the x with 1. So this will be 2 times 1 minus 3 times y, which is 2. And I want to know if that's going to be equal to -4. That's why I put the question mark on top of the equal sign. Now let's simplify the left side. 2 times 1 will be 2, minus 3 times 2, which is 6. I want to know if that's going to be equal to -4. And when I do 2 minus 6, that would give me -4, which is equal to -4. So this is a true statement. So we know the ordered pair 1, 2 is true for the first equation. But what about the second equation, which is 2x plus y equal 4? So here we're going to substitute the x again with 1 and the y with 2. So I got 2 times 1 plus 2. I want to know if that's going to be equal to 4. Let's see, 2 times 1 is 2. And I want to know, is 2 plus 2 equal to 4? And if I add 2 and 2 together, you'll get 4, which does equal to 4. So this is true also for the second equation. Okay. So I know the order pair 1, 2 is true for both equations. That means that it is true for the entire system. So I can say that the ordered pair 1, 2 is a solution. Well, as a matter of fact, it is the solution to the system. Now, what about the ordered pair 7, 6, which is part B? So in this case, here my x is the x coordinate 7, and the y will be that y coordinate 6. All right, so each equation in that system, I'm going to substitute the x with 7 and the y with 6. So for 2x minus 3y equal negative 4, I'm going to substitute the x with 7. So I got 2 times 7 minus 3 times, substitute the y with 6. And I want to know if that's going to be equal to negative 4. Well, 2 times 7 is 14, minus 3 times 6, which is 18. I want to know if that's going to be equal to negative 4. Well, if I do 14 minus 8, I will get negative 4. And as you can see here, both sides are equal, so it is true for the first equation. But what about the second equation, which is 2x plus y equal to 4? Well, the x is going to be 7, so it'll be 2 times 7 plus y, which is 6. I want to know if that's going to be equal to 4. Well, 2 times 7 is 14, and I want to know is 14 plus 6 going to give me 4. And if I add 14 and 6 together, I would get 20. This is what I get, 20 equal to 4. That is definitely a false statement because 20 does not equal to 4. So as you can see here, that ordered pair 7, 6 was true for the first equation, but not for the second. So I can conclude that the ordered pair 7, 6 would not be a solution to the system. So I can just write the ordered pair 7, 6 and just state is not a solution to the system. Okay. All right, so that's how we determine whether ordered pairs are solutions to a given system of linear equations. All right, now let's find the ordered pairs for a solution for a system of linear equations. There are 2 methods that we're going to use here. One will be the substitution method. And in the substitution method, we're going to have to eliminate a variable. And this involves converting the system to one equation in one variable by an appropriate substitution. Okay? So in this case here, we have to do an appropriate substitution. We might either have to get x by itself or get y by itself, and then make that substitution for that variable in the other equation in order to obtain a equation in one variable. That's going to be the point here, or our objective. And as you can see in this yellow box, here I have the procedure for solving a linear system by substitution. First, you're going to solve either of the equations for one variable in terms of the other. Now, if one of the equations is already in this form, you can skip this step. That means if you have x equal to some expression or y equal to some expression, you can skip that step because that variable is already by itself. And then number two, you're going to substitute the expression found in step one into the other equation. This will result in one equation in one variable. Then step three is to solve the equation containing one variable. And then step number four, you're going to do back substitution. You're going to back substitute the value found in step three into one of the original equations. Then you're going to simplify and find the value of the remaining variable. And then step number five is to check your proposed solutions in both of these systems given equations. You have to use the original equation that you start off with in order to do the check. Okay, so like in example 2, we had this. We want to solve by the substitution method. And in this case, we got 2x minus 3y equal negative 13 and y plus 2y, y equal 2x plus 7. Now, what I'm going to do here is write these off side by side. Write these equations side by side. This should be a minus sign, not a plus. So that first equation, 2x minus 3y equals negative 13. And the other equation is y is equal to 2x plus 7. Well, if you look carefully, you'll see that this equation right here already has y by itself. Y equal 2x plus 7. So what I'm going to do here is take that 2x plus 7, which is what y is equal to, and substitute it for y in that first equation. So when I do that, here's what I'm going to have. I'm going to have the 2x minus 3 times y is this, 2x plus 7. So I'm substituting 2x plus 7 in for y because that's what y is equal to. And then I'm going to bring down equals negative 13. And now we're going to simplify all of this because now we get an equation in one variable. So I'll simplify by removing the parentheses and combining some like terms if necessary. So I'll bring down the 2x. Now I'm going to distribute the negative 3 over the 2x plus 7 by using the distributive property. So negative 3 times 2x will be minus 6x. And then negative 3 times that plus 7 will be minus 21. That's equal to negative 13. Combine like terms, you get 2x minus 6x. That's negative 4x minus 21 equal negative 13. And then next, to get negative 4x by itself, I'm subtracting 21, so I need to add 21 on both sides. This will give me negative 4x equals, let's see, negative 13 plus 21 is 8. So negative 4x is equal to 8. And then to get x by itself, we divide both sides by negative 4 to get x equal negative 2. All right, I know what x is. I also need to find out what y is because when I'm solving a system of linear equations, I need an x and a y, which represents the ordered pair that satisfies that system. Well, I know y equal 2x plus 7, and I've solved for x, and it came out to be negative 2. Let's use that y equal 2x plus 7 and substitute the x with this negative 2 in order to find out what y is. So I got y equal negative 2 times negative 2 plus 7. So here, if I do 2 times negative 2, that's negative 4. And negative 4 plus 7 tells me what y is. It'll be 3. So now I have x equal negative 2 and y equal positive 3. So those two values represents the ordered pair that satisfies the system. So the solution written in the form of an ordered pair would be x comes first as negative 2, and then y comes next. That would be 3. So negative 2, 3 is the solution to that system. Okay. Now, step number 5, I will leave up to you for the sake of time. But if you do the check, you can see that in this case, 2 times negative 2, that'd be negative 4. And then minus 3 times the 3 will be minus 9. So negative 4 minus 9 would give you negative 13. And then the last equation, y equal 2x plus 7. Well, if I do 2 times negative 2, that's negative 4 plus 7 would give me 3. And of course, y equal 3. So we can say for certain that the ordered pair negative 2, 3 is the solution to that linear system. Okay, here's another example. Let's say we have something like this. 3x plus 2y equal 4, and 2x plus y equal 1. Again, I'm going to write these side by side. 3x plus 2y equal 4. And the other equation would be 2x plus y equal 1. Now notice the x, neither the x nor the y is by itself. So we're going to try to get either x or y by itself. Now, the best advice I can give you for that would be to get the variable by itself. And I'm dealing with the variable that has the coefficient of a 1. Okay, it's best to get the variable that has a coefficient of 1 by itself. Okay, that way you won't have to deal with a lot of fractions here. Like in this one, 2x plus y equal 1. Okay, if I was to get x by itself, I'm going to be dealing with a lot of fractions here. And if I dealt with that first equation, I would definitely be dealing with a lot of fractions because I had to either divide all the way through by 3 or divide all the way through by 2. So let's work with the one that has a coefficient of 1 for the x or for the y, like this 2x plus y equal 1. We're going to get y by itself. I'm adding 2x, so the opposite of that would be to subtract 2x on both sides. So here I'm going to have y is equal to 1 minus 2x. Okay? Keep in mind the 1 and the minus 2x are unlike terms. Okay, so I do have a variable by itself. In this case, I have y by itself. Here's what I'm going to do. Since y is equal to 1 minus 2x, I'm going to take that 1 minus 2x and substitute it for y in the first equation. Hence, that's what we call this substitution. So I'm going to bring down the 3x plus 2 times that y will be substituted with this expression, 1 minus 2x. And that's equal to 4. So now I have an equation in one single variable. So I'm going to remove the parentheses and combine like terms here. So I'll bring down the 3x, and then plus 2 times 1 would be plus 2, and then 2 times minus 2x would be minus 4x, and that's equal to 4. And then combine like terms here, 3x minus 4x would be minus 1x, and then plus 2, and that's equal to 4. And then get negative 1x by itself, I'm adding 2, I need to subtract 2 on both sides. So that means I'm going to have negative 1x equals 2. And then divide both sides of this equation by negative 1 because I want positive x. So x in this case will equal negative 2. Now, I only solve for x. I need to find out what y is. Well, y is equal to 1 minus 2x. And I know x is -2, so what I'll do here is substitute this x in the y minus 2x with -2. So here's what I'm going to have. Y is equal to 1 minus 2 times, replace the x with -2. So y is equal to 1, and then minus 2 times -2 will be a plus 4. And then 1 plus 4 ends up being 5. So in this case, y is equal to 5. So my solution to this system would be the ordered pair -2 and 5. Okay. All right, so that's how we apply the substitution method to solve a system of linear equations. All right, next we'll look at another method of solving a system of equations, and that is the use of the elimination method. Well, on this handout, it says the addition method, but the way to, in some textbooks, call it the elimination method, by the way, because you're going to have to add or subtract the two equations in order to get an equation in one variable. Okay. So here the addition method involves eliminating a variable and ultimately solving an equation containing only one variable. So here we eliminate a variable by adding the equation so that the sum is an equation containing only one variable. So here the key step is to obtain for one of the variables coefficients that differ only in sign. And to do this, we may have to multiply one or both equations by some non-zero numbers so that the coefficients of one of the variables, x or y, become opposites. Then, when the two equations are added, this variable is eliminated. Okay? So with this, that's sometimes is called the elimination method in some textbooks. And here's the procedure for solving a linear system through addition. And that's this. If necessary, you need to rewrite your equations in the form of ax plus by equals c. In other words, you need the x and the y on one side and the constant term on the other side. And then number two, if necessary, you may have to multiply either equation or both equations by an appropriate non-zero number or appropriate non-zero numbers so that the sum of the x coefficients or the sum of the y coefficients is 0. Because you have to be able to eliminate either the x or the y when you combine those two equations. And then number three is to add the equations in step 2. That sum should be an equation in one variable. And then next you're going to solve the equation in one variable. And then step number 5 is to back substitute the value obtained in step 4 into either of the given equations and solve for the other variable. And then finally, step number 6 is to check your solution in both of the original equations. So that's the procedure for solving a system of equations using the addition method. Okay, so now let's look at example 4. And that is to solve the equation by the addition method. And in this case, we got 3x plus 2y equal 14 and 3x minus 2y equal to 10. So I'm going to write the equations here. Let's see, 3x plus 2y equal 14. 3x minus 2y equals 10. Now we're going to use the addition method. Okay, and this is going to be an easy want to do, because notice we already got plus 2y and minus 2y. Those are opposites. So we can add those two equations directly, okay? So what's going to happen here is when we do that, the plus 2y and the minus 2y are eliminated when we combine those. So that means we're going to have 3x plus 2x is 6x equals 10 plus 14, or 14 plus 10. That'd be 24. And as you can see, we do have an equation in one variable. 6x equals 24. And from here, we can solve for x. We're multiplying by 6, so I need to divide both sides by 6. So that means x is equal to 24 divided by 6 will be 4. So I know what x is. It's equal to 4. Now I need to find out what y is. Now, here I have a choice to use either the first equation or the second equation and substitute the x with 4 and simplify. I'm going to go ahead and use the first equation. Now, if you wanted to, you can use the second equation. So here I'm using 3x plus 2y equals 14. And then I'm going to substitute the x with that 4, because that's what x is equal to here. So substituting, I have 3 times x, which is 4, plus 2y equals 14. And then do 3 times 4, that will be 12. And then plus 2y equals 14. And then to get 2y by itself, I'm adding 12, so I need to subtract 12 on both sides of this equation. This will mean 2y is equal to 2. And then to solve for y, we'll divide both sides by 2. Y is equal to 1. Okay? And now y is equal to 1 and x is equal to 4. So that means I have my solution to this system of equations. And it is the ordered pair 4, 1. Again, x comes in, goes first, the y follows after it. Okay. All right, now let's take a look at another example. Let's say we have a system of equation like this one, 4x plus 5y equal 3, and 2x minus 3y is equal to 7. Now, if we were to combine these two equations together, there's no way we're going to eliminate either the x or the y. So this is a case where we need to multiply one or both equations by a non-zero number. All right, so now let's rewrite our equations. All right, in this case here, let's see what variable we can eliminate. Now, this is what I would do. This is just me. I'm going to eliminate the x's because I see something here. This 4 in front of the x is a multiple of this 2 in front of the x. Okay. So here, the best way to do this is find the least common denominator of the coefficients of x or the coefficients of y. Like in this case here, my coefficients of x are 4 and 2. And the least common multiple is the smallest number that is divisible by 4 and by 2. And in this case, it's going to be 4 because I know 4 is divisible by itself and 4 is divisible by 2. So we have to look for some least common multiple, either for the x coefficients or for the y coefficients. And since I'm trying to eliminate the x's, I'm using 4 and 2. Now you could have used the 5 and the 3 as for those coefficients in your y, because there's a plus sign and a minus sign. But I'm going to show you why I did that. Because notice I got a 4 in front of the x. So I don't need to multiply this top equation. However, I need to multiply this bottom equation. Because if I want this to be 4x, and if I want that to be negative 4x, because I need to eliminate the x's, so one would be plus and the other one would be minus, I'm going to multiply that bottom equation by -2. And why negative? Because one has to be a positive 4x, the other one has to be negative 4x. Okay, so this is what I'm going to have. I'm going to bring over the 4x plus 5y equals 3. But when I multiply all the way through by -2, this is what I have. -2 times 2x will be -4x. -2 times the plus 3 minus 3y would be a plus 6y. And that's equal to -2 times 7 would be -14. Notice I have the opposite of 4x and the opposites of 4x, positive 4x and negative 4x. When I combine those two, they're gone. The x's are eliminated when I combine those two. And now when I have 5y plus 6y, add those together, you'll get 11y equals 3 plus -14, -11. Okay, and I think I made a mistake somewhere. Let me double check. Multiplied by -2 is -4x plus 6y and then -14. Okay, I'm okay. So 11y is equal to -11. And then to solve for y, we divide both sides by 11. You'll get y is equal to -1. So here y is equal to -1. Now I need to find out what x is. In this case, I can take either the first equation or the second equation and replace the y with -1. I'm going to use the second equation, which is at 2x minus 3y equals 7. And then substitute the y with -1. So this will be 2x minus 3 times y, which is -1, equals 7. So now minus 3 times a -1 will be a plus 3. So it'll be 2x plus 3 is equal to 7. And then to get the 2x by itself, we subtract 3 on both sides. You'll get 2x equals to 4. And then finally divide both sides by 2 to solve for x. So x is equal to 2. So as you can see here, x is equal to 2 and y is equal to -1. That's the ordered pair for this solution to the system of linear equations. It's the ordered pair to -1. Now, let me mention this. Had I tried to eliminate the y, since I have a plus and a minus here, I would have to multiply the top equation by 3 and the bottom equation by 5. But I'll still come up with the same solution here. Okay, now next we're going to look at something that might be a little bit more complicated, like this one. If the value of one variable turns, if the value of one variable turns out to be a messy fraction, and it could happen, it'd be best to back substitute. Well, back substitution will give you some cumbersome arithmetic. Okay. Now, what we can do here is return to the original system and use the addition method to find the value of the other variable. Okay. Now let's look at example 6 here. It says here, solve by the addition method. We have 2x equal to 9 plus 3y, and 4y is equal to 8 minus 3x. This is one of those cases where you're going to be dealing with some messy fractions here, and substituting for x or for y can be cumbersome because you have to find the least common denominator and go through all of that simplification to come up with the value of the other variable. Okay, so let's start by doing this. We need the equations to have the x and the y on one side and the constant term on the other side. So for the 2x equal 9 plus 3y, I need to move the 3y over to where the 2x is. And when I do that, it'll be minus 3y. And then that's equal to 9. And then for the second equation, 4y equals 8 minus 3x, I need to move the minus 3x over to where that 4y is. Well, if I move the minus 3x over to the other side, it will be a plus 3x, and then plus 4y equals 8. So here, both of those equations are written in standard form, where the x and the y is on one side and the constant term is on the other side. All right, so first, let's see here. Since I have a minus 3y and a plus 4y, let's try to eliminate the y's. And to do that, I need a least common multiple of my coefficients, 3 and 4. That will be the smallest number that is divisible by 4 and by 3. And in this case, it is 12. Now, if you didn't know that, you can list all the multiples of 3 and all the multiples of 4. You'll see that 12 is the smallest multiple that can be used here. Now, I'm going to rewrite this. The 2x minus 3y equals 9, and 3x plus 4y equals 8. All right, so, and my least common multiple is going to be 12. Okay, so if I want that minus 3y to be minus 12y, I need to multiply that top equation by 4. And for the bottom equation, if I want that 4y to be 12y, I need to multiply its equation by 3. All right, now another way you could have done that would be this. If you're eliminating your y's, this 4 would be multiplied by the top equation, and that 3 would be multiplied by the bottom equation. In this case, you don't worry about the sign because I've already got a minus and a plus. And that's what I want. Now, if both of them were plus signs, then either the 4 has to be negative or the 3 has to be negative. Now, I'll show you that in a few minutes. All right, in the meantime, if we multiply that top equation by 4, this is what I'll have. 4 times 2x is 8x, minus 4 times 3y, which is 12y, equals 4 times 9. That'd be 36. And then for the second equation, 3 times 3x is 9x. 3 times 4y would be plus 12y. That's equal to 3 times 8. That'd be 24. And now we can combine the two equations together. You'll see that minus 12y and plus 12y are gone. They're eliminated. And then we combine 8x and 9x is 17x. Equals 36 plus 24 is 60. So I have 17x is equal to 60. But when I divide both sides by 17, you're going to get x is equal to, and we'll leave this as 60 over 17. Now, this is where you get a messy fraction, because if you were to substitute for x in either one of these equations, you're going to have to manipulate that equation in a way that you're going to have to find probably a least common denominator and come up with equivalent fractions to come up with what y is. Okay, so this is where we go to the original system and try to eliminate the other variable. We found out what x is by eliminating the y's. Now we're going to find out what y is by eliminating the x's. So here's what we got. I'm going to rewrite those equations that are in standard form. 2x minus 3y equals 9, and 3x plus 4y is equal to 8. Now we're going to try to eliminate the x's. We need a least common multiple of 3 and 2. That's the smallest multiple that is divisible by 3 and by 2. In this case, is 6. Now, if I want this 2x to be 6x, I need to multiply the top equation by 3. And for the second equation, the bottom equation, if that 3x is going to be 6x, I need to multiply it by 2. However, just a positive 3 and a 2 will not eliminate the 6x's. One has to be negative, the other one has to be positive. So here, by choice, I'm going to make the 3 negative. So here, if I multiply the negative 3 times 2, this will be negative 6x. Negative 3 times minus 3y would be plus 9y equals negative 3 times 9, negative 27. Now for the second equation, I'm multiplying it by 2. So 2 times 3x is 6x. 2 times 4y would be plus 8y equals 2 times 8. That'd be 16. All right, so when I combine those two equations, the 6x's are gone. They are eliminated. So now 9y plus 8y is 17y equals negative 27 plus 16 will be negative 11. So I got 17y equal negative 11. Then divide both sides by 17. You'll get x is equal to negative 11/17. Okay, so I know what x is and I know what y is. So I do have my solution to the system of linear equations. It'll be the ordered pair of 60 over 17 and negative 11 over 17. And I'm not going to even worry about doing the check for the sake of time, because that can be some cumbersome arithmetic as well. Okay. Here's another example where you do have some cumbersome arithmetic where your x is going to be in the form of a fraction. Okay, so let's say you want to solve this by addition, by the addition method. Here we got 2x is equal to 3y plus 4, and 4x is equal to 3 minus 5y. Both of these equations need to be written in the form where all the x's and the y's are on one side and the constant term is on the other side. So for that first equation, I need to move this 3y over to where that 2x is, and it'll become minus. So I got 2x and then minus 3y equals 4. And then the second equation, 4x is equal to 3 minus 5y. Move the minus 5y over to where the 4x is. This is what I'll have. 4x plus 5y equals 3. Okay, so here are all the x's and the y's on one side and the constant terms on the other side. Now again, if I try to add those two equations, I'm not going to be able to eliminate either the x or the y. Okay, so now let's think about this for a moment. We can eliminate the y's here because I have a minus and a plus in front easily. So here I need a least common multiple of 3 and 5, which is in this case going to be 15. Okay, so I'm going to write my equations over 2x minus 3y equals 4, and 4x plus 5y equals to 3. And I'm eliminating the y's. So if I want that 3y to become minus 15y, I need to multiply that top equation by 5. And for the bottom equation, if that 5y is to become 15y, I need to multiply that bottom equation by 3. So now, when I do that, I have 5 times 2x, that's going to be 10x. I'm multiplying the top equation by 5, minus 5 times 3y, which is 15y, equals 5 times 4, that's going to be 20. The bottom equation, I'm multiplying it by 3, so 3 times 4x is 12x, plus 3 times 5y, that's 15y, equals 3 times 3, which is 9. Okay, so combining these two will cause the 15y and the minus 15y to be eliminated. And then if I add 10x and 12x, that's 22x equals 20 plus 9, 29. So I got 22x is equal to 29. But when I divide both sides by 22, I'm going to get a fraction. X equals 29 over 22. So here, substituting x in one of the equations with 29 over 22, the arithmetic can be complicated. So now we eliminate the y's. Let's try to eliminate the x. So we go back to our 2x minus 3y equal 4, and 4x plus 5y is equal to 3. Now, we're eliminating the x's here. Well, we need a least common multiple of 2 and 4. And that's going to be easy because that's just going to be, actually it's going to be 4. Because 4 is divisible by itself and 4 is divisible by 2. So in this case here, if I want that 2x to be 4x, I need to multiply that top equation by 2. However, if I want that 4x to be eliminated, this will be a plus, the other one has to be negative. Has to be. Because I have to have one of them to be negative, the other one has to be positive in order to eliminate. So let's just make the top equation, multiply that top equation by -2 instead of a +2. And when I do that, -2 times 2x will be -4x. -2 times -3y will be a +6y. That's equal to -2 times 4, -8. And then bring over the second equation, 4x plus 5y equals 3. Now when I combine those two, -4x and 4x are gone. 6y and 5y added together is 11y. That's equal to -8 plus 3, -5. So I got 11y equal -5. Now when I divide both sides by 11, this would mean y is equal to -5 11ths. So here, I know what x is and I know what y is. So I do have my solution to this system of equations, and it's in the form of a fraction. 29 over 22 and -5 11ths. Okay. So this is just a couple of examples that I just did where you have to first eliminate one variable and you end up getting x with a fraction. And then you have to go back to the equations in standard form and then eliminate the other variable to solve for, in this case, y. Okay, now let's talk about linear systems that have either no solution or infinitely many solutions. Now, two lines either intersect at a point, are parallel, or are identical. Okay. Now, the ones that we just did in these few examples were equations where the lines intersect at a point. Okay. Because if you were to graph this on a coordinate plane, it may be difficult for you by sight to see where the ordered pair where those two lines intersect to come up with that exact ordered pair, which is why we do the substitution and the elimination methods in the first place. Okay, so this is where these two lines intersect at a point. You're going to have exactly one solution. Now, no solution is where the two lines are parallel, as you can see here. That means that anything parallel means that the two lines are not going to intersect anywhere. And then finally, infinitely many solutions would mean that one line lies on top of the other. The two lines are identical. Okay. All right, now let's look at some cases where you may have something like this, an inconsistent system. Now, an inconsistent system means this. It's a linear system with no solution. That means that both variables will be eliminated and you'll end up with a false statement like 0 is equal to 12. And if you have an inconsistent system, that basically means that if you were to graph your lines on a coordinate plane, those two lines will not intersect anywhere. They're just going to be parallel. Okay, so it does go back to this right here. The lines will be parallel. That means there's no solution. It's going to be an inconsistent system. Like in this example here. Let's say you want to solve the system 5x minus 2y equal 4 and negative 10x plus 4y is equal to 7. Okay. I'm just copying those two equations over. Now, in this case, let's try to eliminate the x's because I have a plus sign and a negative sign. I can eliminate those easily. And I do need a least common multiple of those coefficients for x, 5 and 10. That's easy. That's going to be 10 because 10 is divisible by 5 and 10 is divisible by itself. So now, for that first equation, to make 5x 10x, I need to multiply that entire equation by 2. And that's basically all I need to do there because I've already got minus 10x, so that's okay. multiply that top equation by 2, it'll be 2 times 5x, which will be 10x, minus 2 times 2y will be 4y, equals 2 times 4, which will be 8. And I'll bring over the second equation, negative 10x plus 4y equals 7. Now watch what happens when I add those two equations together. Notice that 10x and minus 10x are gone. Also notice this, minus 4y and plus 4y. They're also gone on the left side. I'm left with nothing, or 0. And that's equal to 8 plus 7, which is 15. Notice I have a false statement. 0 does not equal to 15. So this is a false statement. So that means this system of linear equations is considered to be inconsistent. And if it's inconsistent, that means your system will have no solution. Okay? Because inconsistent systems have no solution at all. And if you were to graph those two lines on a coordinate plane, they're not going to intersect at a point at all. That means the lines are parallel. Okay. All right, next is a consistent system. All right, a consistent system by definition is a linear system that has at least one solution. So that means that the lines will intersect or coincide. Now, the ones that we did earlier were lines that intersected at a single point. Those are considered to be consistent systems. And sometimes they're called consistent and independent. Okay. Where the two lines intersect at a single point. Consistent and independent. Okay. There's also something called consistent and dependent, meaning this. The equations in a linear system have infinitely many solutions where the lines coincide. In other words, the lines will lie on top, one line will lie on top of the other. And this is where both variables are eliminated and you'll get a true statement like 10 is equal to 10. So for such a system like this one, x is equal to 4y minus 8 and 5x minus 2y equal negative 40. And I want to solve this system. Okay, here's what I'm going to do. I'm going to write x equal 4y minus 8 on the left side and 5x minus 20y equal 40 on the other side. All right, notice I got x is equal to some expression, 4y minus 8. What I can do here is use the substitution method. Okay, so sometimes you may have to use whatever method that will be best for you to solve a system of equations. In this case, it would be best to use the substitution method. So I can take that 4y minus 8, which is what x is equal to, and substitute it for x in the other equation. So in this case, I got 5 times, and I'm substituting the x with 4y minus 8. Then minus 20y equal negative 40. And then simplify it by combining like terms. 5 times 4y will be 20y. Minus 5 times 8 will be 40. Then minus 20y equals negative 40. Now, when I combine like terms, here the 20y and minus 20y, they are gone. So now I'm left with negative 40. And that's going to be equal to negative 40. Notice I came up with a true statement because negative 40 does equal to negative 40. So this is a case where this system of linear equations will be consistent and dependent. And a system that is consistent and dependent means this: I'm going to have infinitely many solutions. And also, if you were to graph this on a coordinate plane, you'll find out that the lines will coincide. In other words, the line of this first equation will lie on top of the line of the second equation. And by the way, if you were to look at those two equations carefully, they're actually the same. And with the exception, this first equation, if you were to multiply it by 5, you would get this second equation right here. Multiply the first equation by 5, you'll get the second equation. So that second equation is the same as the first equation in disguise. Okay. All right, so that will conclude this video on section 5.1, dealing with systems of linear equations in two variables. Do feel free to email me if you have any questions about the homework in my math lab, or any questions about the examples that were discussed in this video.